It's my pleasure to introduce Ruijia Wang, our seminar speaker today. Ruijia received her PhD in seismology from the University of Canada in 2018, and she was a postdoc University of Western Ontario and also University of New Mexico. She's currently in New Mexico right now, and really happy to say that she's been appointed assistant professor at Southern University of Science and Technology in China, and so that begins in December. Ruijia's interest is earthquake source processes, mostly focused on induced seismicity and hydraulic fracturing. She's worked on just general seismic source problems, micro-earthquake finite source problems, seismic discrimination, identifying different classes of seismic events, and studying the state of stress in these induced seismicity environments. And so today, she's talking about complexity and simplicity of injection-induced earthquakes in the Raton Basin. So thank you very much, Ruijia, and you have the floor.
Sweet. Everyone hear me okay?
Okay.
Cool.
Very good.
Well, thank Doug for the kind invitation. And like mentioned, New Mexico here is pretty dry, and that's actually because of weather, lack of rainfall. But the fault system in the northern part is pretty wet, and that's because of wastewater injection. So in the coming 40 minutes, I will share our source study in this small region about the injection-induced earthquakes in the Raton Basin. And also looking forward to discussing with you about the complexity and simplicity of these man-made earthquakes. So background first, what exactly is induced seismicity and why so serious? Induced earthquakes are events that are triggered or induced by industrial activities, which usually involves fluid injection or extraction. Others may be mass removal, like mining. The magnitude of induced earthquakes are often between 0 to 5, and several larger ones up to magnitude 6 happen in the past few years. But luckily, the majority of the induced seismicity are relatively small and did not cause much damage. The map here showing the slide collects and highlights the relatively large, potentially induced earthquakes all over the world. So the colors here corresponds with the reasons listed on the right side. I would like to point out just a few of them. It's been over a decade since the devastating Wenchuan earthquake, which was suspected to be linked with this Zipingpu Dam. And the magnitude 5 wastewater-induced earthquakes in Oklahoma are well known. They are likely the largest ones for wastewater injections. And the largest hydraulic fracturing-induced earthquake used to be the Canadian one, but the record was just set by Raton Basin in 2019. If you have no idea where is that province, that's Panda's hometown. So induced seismicity is a global phenomenon with significant number and moderate magnitudes, and this is why some seismologists care about them. However, the impact and interest of induced seismicity sometimes goes beyond the scientific community. For regions like Alberta, Canada, where I spent years for my PhD degree, earthquakes are rare, and local residents got shocked when magnitude 4-ish earthquake occurred. We got tons of news exposures after such events. And if a magnitude reaches 5, like Raton Basin, damages may occur and we may face life risks. And that's partially because the houses or apartments are not designed to experience such strong shakes from such 5-ish earthquakes. And even for regions that building codes are restrictive, you're not that lucky as well. So the study here on the right side shows the house price could go down because of higher seismicity risk. And this is exactly what happened in Oklahoma. So induced seismicity is impacting our society from daily news to individual life to regional house price. And from a regulation aspect, induced seismicity is also impacting the industrial activity, because the companies have to shut down operation if an earthquake with a certain magnitude occurs. And this is demanded by the traffic light system. Of course, the tolerance level varies from region to region, and this is related to multiple factors like population density. And those 3 hydraulic fracturing wells were shut down after magnitude 4-ish earthquake in the past several years in Alberta. And the news titles here on the right side are just more examples of such extreme cases in European, where the geothermal or gas field are closed due to induced seismicity risks. And the bottom one here on the right is just Sweden temporarily closing this Kairula mine after a magnitude 4.1 event last year. Except mining, geothermal, and gas exploration, another major and famous cause of induced seismicity is wastewater disposal. So although conventional and unconventional resource exploration is producing wastewater, and there are actually other sources that add to the pool as well. So because wastewater have kind of steady and multiple resources, it usually have a large volume and the injection lasts for months or even years. Therefore, much more fluid is injected to the underground, and the potential to induce larger magnitude earthquake is also slightly higher. So before I jump to the wastewater-induced events in Raton, here's a very quick recap of such seismicity in the central United States. Some of you may be familiar with this already. The discovery of induced seismicity wasn't new. People know this since 1960s. While induced seismicity become popular, likely around the time of this publication by Bill Ellsworth. And here the figure in the bottom is just an updated figure showing the number of magnitude larger than 3 earthquakes in central US that is really boosted in red in the past decade. And central US here is defined by the map view here on this intraplate region. Where in this map, the potentially tectonic earthquakes are in blue and the likely induced ones are in red. So in fact, the number of magnitude larger than 3 earthquake in Oklahoma exceed that for California for a couple of years. I think it's around 2015. So it's just was beat by the Ridgecrest earthquake 2 years ago. So anyway, the increase of the seismicity and the number of these larger, relatively larger or moderate earthquakes are the driven fact for the growing studies on induced seismicity. And when we talk about magnitude larger than 5 events induced by wastewater disposal, a lot of you immediately think about Oklahoma, events like Pawnee and Cushing earthquakes. That's correct. So the map here on the left side actually show these elevated induced seismicity, elevated seismic hazard kind of like caused by the induced seismicity, which magnitude 5H earthquakes have the major contribution to that. However, Raton Basin also hosted a magnitude 5 earthquake. And then this is shown by this diamond shape here. So all in the map on the left side, all these polygons are indicating regions with significant induced seismicity, seismic risk increase. And let's just look at where we're gonna focus today about the Raton Basin. Raton Basin is a targeted region for methane extraction, and all the wastewater produced during the exploration of methane are injected back to this region at depths around 1 kilometer. And maps here on the left side shows an earlier study of these earthquakes. The detailed contour of Raton Basin here is shaded in green on the left side. So it extends for about 50 kilometers from north to south, and is about 30 kilometers wide from east to west. The tiny yellow triangles here are showing where the injection wells are. The wells are pretty shallow, mostly within the basements, above the basements. So also shown in this figure, the beach faults that have been resolved for previous seismicity. And the red one here marks the magnitude 5.3 earthquake that happened back in 2011. The figures here on the right side are from Rubinstein et al. So I won't go into the details, but just by looking at the earthquake rate, the blue bars, and the injection, the red lines, you could be confident about the induced nature of these events here in both the Colorado side and the New Mexico side. So before 2016, seismic monitoring in this Raton region relies on probably just one broadband station, which is this blue triangle here on the edge of the basin. And in 2016, our group at the University of New Mexico deployed 7 more broadband stations shown by the green triangles here. 3 of these 7 stations are telemetered to ARIS data center, and these providing the fundamental seismic coverage or monitoring for this region. And also these are the stations that led to the location of the red stars here. However, we look at this spatial distribution of these stars, they seem pretty scattering, right? They are not aligned along any lineament, which means we cannot tell what the fault looks like in this region. And another curiosity we had is the normal fault that used to host this 5.3 earthquake still active, or did it come down after 2012 or 2013? It seems seismicity rate still persists in this region. So is that fault really shut down, or is just our detection ability cannot see the events? And if that particular fault did shut down, where are the other faults being so productive? To solve these questions and learn about the faults that host induced seismicity here, a nodal array with 96 three-component sensors were deployed in the southern part of Raton Basin, and most of them are in the New Mexico side. These are deployed in the summer of 2018. Here on the right side, the zoom-in figure shows the location of these 96 nodal stations, the brown triangles here. Their battery could support high-frequency recordings like 250 Hertz for about a month, and there are all three components. So during the nodal deployment months, only 2 earthquakes were reported by USGS, and they are marked by the red star here, one in June to the north and one in May to the south. The blue squares here, again, are the wastewater injection wells. The size of these wells are scaled with their monthly injection volumes, which is about 200,000 barrels per month on average. And I hope all of you agree with me that picking seismic phases could be very boring. If any of the geeks disagree, let's say at least it's very time consuming. So picking nearly 100 three-component stations or 8 broadband over a 4-year period, like the setup we have, could be very time consuming. So we adopted a machine learning phase picker to identify the P and S arrivals for us. Some of you may be familiar with this package, FaceNet. FaceNet was developed by Ju and Barroza in 2019, and it was trained using a 30-year catalog in Northern California at a sampling rate of 100 Hertz. The outputs of FaceNet are the P and S arrival probabilities. You can think about this probability parameter as a confidence level ranging from 0 to 1. So one issue or challenge we have is about the study scale. As I highlighted here on the right side in the map, the training data was obtained from Northern California at a scale of a few hundred kilometers. Such training data set is actually an order larger than our nodal array distribution here. And our targeted magnitude are a few magnitudes smaller too. So in ideal cases, we should apply transfer training, but unfortunately, we don't have any source of the pickings on hand to do that. So to address this mismatch in scale, we decide to run FaceNet for our data set with the original sampling rate about 250 Hertz. The change of sampling rate seems inconsistent with this training parameter. But if you believe that earthquakes are self-similar, say a magnitude 1 event is just a compressed version of magnitude 3 in time and space, the decision isn't too crazy. The machine learning package reads whatever fed it to it as a time series without a sense of time scale. And it turns out, after rescaling, FaceNet worked pretty well for our region. As a result, we obtained 5 million P arrivals and 8 million S arrivals with probabilities higher than 0.5. Our experience from the broadband array shows even the ones with probability as low as 0.3 seems trustworthy. So with millions of the arrivals on hand, we use a program named REAL, Rapid Earthquake Association and Location, to associate the individual arrivals and turn them into seismic events. The association procedure results in over 10,000 earthquakes with rough locations, here shown on the left side. Then we go through accurate location using VLAST, and then finalize our detection with HypoDD, double difference relocation. The numbers here in the upper right corner represent the number of events we retain during each of the steps. And over 90% of the earthquakes survived these refining steps. And this high survival rate also validates the robustness of our phase picking. If you look at the color bar here on the right side, most of these earthquakes are located around 4 to 6 kilometer depths, so they are within the basement. We will look at the spatial distribution of them more closely in later slides. So let's check the temporal distribution of them first. The figure here shows these events along the time scale. So the y-axis here is magnitude. Do you still recall the two events reported by USGS? This is the June one, and this is the May one. These are magnitude about 3, and all the events below them are our new detections. And their magnitude goes down to -2. That's as small as macro seismicity. And this is what a magnitude -2 event looks like recorded by stations within 2 kilometers. These are raw SAC waveforms, and the blue one indicates the P window, where the red one is the S window. I'm also labeling the S wave probabilities from FaceNet. And here a typical value is 0.75, a relatively high case, and a relatively low case, probably the worst case we are using. And coming back to the time plot, you may notice I shaded that. So the light orange bars here actually represent daytime in our local hour, so mountain time. And if you look closer, you may notice that the minimum magnitude varies with day and night times. We're looking at a magnitude of completeness close to -1 during the night, the white parts here. And we're looking at the magnitude of completeness close to -0.5 during the daytime, the yellow parts. In other words, our detection number is higher and detection ability is better during the nighttime. Why? Why do we have a 24-hour detection cycle? Well, we come up with 4 potential causes as listed here on the right side. We could walk you through and just almost exclude the first 3. So the Raton Basin have very low population, likely less than the number of audiences we have in this Zoom meeting. So you guys or human activity won't be able to affect our detection systematically this much. And similarly, we could exclude industry activity as a reason, since the pumping or extraction of methane goes days and nights. The pump jacks don't take night shifts. And solid earth tide could be a very good guess, but we did not see any 12-hour period. We only observed the 24-hour one. And since our nodal array is only out for a month, we cannot identify any longer period patterns like the monthly cycles. So it turns out the last reason here explains the 24-hour period pretty well. So the figure here shows our hourly detection rate in gray, averaged from the 33 days, and the pink bars here on top are the average hourly wind strengths in the Raton Basin. The arrow bars are the variation of them divided by 5. And here I'm also drawing a little sun in the daytime and shade our sunshine across the day. If we calculate the cross-correlation coefficient between the number of detections and the wind strengths, the value is close to -0.8. Therefore, we are very confident to say that our detection ability is modulated by the wind strength or the noise level. Now let's come back to our initial target, the fault system that hosts the induced seismicity in the Raton Basin. We also know that the fault planes are never simply planary. In the following slides, I will show you how complex the fault system could be in a small region like Raton. And here's the figure.
Ruijia, can I ask a quick question about the wind noise?
Yes.
So is it loading on trees, or I don't know, but I don't know enough about the geography there. Is it loading on towers?
I think it's just grass and nothing else.
It's
the
grass.
vegetation.
So the wind going across the surface of the ground with like a sage.
Yes, because the nodal, the sensors are just at the surface. We didn't really borrow them.
So you don't see any resonances. I guess that's what I was getting at.
Probably Brandon could answer that question because I wasn't really in the field much. But to the best I know, no, we don't really have a lot of resonance of human or animals that regularly have this any activities out there.
Can I also ask a question?
Yeah.
Hi, Ruijia. So here you make a cross correlation between the magnitude of completeness with the wind noise, but I think there is a certain gap here. It's better to check the noise level from the raw data to see whether the noise level is high when the magnitude of completeness is high, and what's the noise level, and what's the frequency of this noise, and whether you have the daily variation of the noise level from the spectra, and by which you can guess like whether it's wind or not, or some other noise, and what's the frequency band, whether it's caused by the tree or the grass. So yeah, that's what I'm thinking. Yeah.
I think you are right. I probably didn't investigate that in detail about the frequency band, but I did cut out the pre-P noises specifically for the small magnitude events, and then compare that between daytime and nighttime. And we did notice they are like 1 to 2 magnitude lower. If you look at the gray bars, these are the pre-P noise levels. They're pretty quiet during the nighttime. If you look at how the bars are shifted. Does that answer your question? Like I mentioned, I don't have a detailed analysis about the frequency, and maybe you should look at the trees.
Okay, yeah, because you make a really detailed like analysis about where the noise come from. So I think it's better to investigate from the raw seismogram instead of the magnitude of completeness, because that may be affected by multiple things. Yeah,
That's very well. Thank you. Should I continue from there?
Yeah, please continue.
Thank you.
Cool. Well, I guess here is a place where you start to look at the spatial distribution of our detections. And like I mentioned, the figure here in the middle are the same map view for our detection, but I switched from the latitude, longitude to the distance in kilometer. So all the cluster shapes are to ratio. And from the map view, we can see these events clearly divided into different clusters, and I'm labeling them from 1 to 4 in this case. Please just pay attention to the color convention and then indexing, because we're gonna keep this color convention throughout my talk in the following analysis. And this is how we define the clusters and examine them. And as I mentioned before, previous earthquake studies suggest a normal fault region, and our results support that. For example, cluster 3 here in the south is also the most productive cluster that hosted about half of the earthquakes during the nodal months. And from the event location distribution, here, the tectonic cluster, you can fit a fault plane orientation about 14 degrees from the north. And this is exactly one of the fault plane that we could resolve from moment-tense inversion, the beach ball here. From the depth views, we believe this normal fault for cluster 3 is sitting at a depth close to 3 kilometers below the basement. And moving to cluster 2 here is more interesting. The cluster is barely studied. I guess that's due to the previous seismic monitoring resolution cannot tell it apart from cluster 1 or 3. But why do we label it as an individual cluster? Well, first, it is spatially separated from the rest. If you look at the depths, cluster 2 is much deeper than the other, sitting around 6 kilometer depths. And more importantly, the moment-tense solution here suggests cluster 2 actually occurred on a different type of fault. It is either a north-south aligned dip slip or east-west aligned shallow dipping strike slip. So as you could tell from this central figure already, the faults in the Raton Basin, even though they are dominated by normal style, they do vary from cluster to cluster. And to better examine the fault geometries, we could further refine our location. Specifically, we could give a higher weight to the ice arrivals to better constrain the depths. We can also run cross-correlation based detection and locations for them. And here on the left side is just the same figure from the map view with more beach balls on them, where the figures here in the center are really zooming into cluster 3 and cluster 4. So here in the middle, I'm showing the map views again, but zoom in, whereas on the right side, I'm showing 2 depth profiles looking north. And they are color-coded by time. So from these zoom-in figures, we can see a very clear spatial temporal evolution for these 2 clusters. And we see the events migrate toward from the northeast toward the southwest for cluster 3. And this is also true for cluster 4, migration within 0.5 kilometer. And we also see this migration along the depth profiles. And the difference between the two clusters, even though they are only separated by a few kilometers, we are looking at some eastward dipping for cluster 3, whereas this normal fault system is actually dipping toward the west side, moving north to cluster 4 here. So we are looking at the migration speed less than a kilometer a week. And if we do a very quick and simple dirty plume stress modeling, we may notice most of these earthquakes follows the distribution of positive plume stress changes, which means they're kind of like triggering each other, just like tectonic sequences. We're still investigating these spatial patterns. And I want to draw your attention to cluster 1 here at the boundary of New Mexico and Colorado. You may notice there's some variation in the beach ball styles again. So we are not very sure if these fault segments are connected to each other, as they're only, most of them are less than 2 kilometers long. But I think by looking at clusters 3, cluster 4, and cluster 1 here, we are pretty confident that we may have some potential conjugate normal systems sitting in this Raton Basin. And you may notice I left cluster 2 out on this slide. Actually, we find more complex behavior for this newly discovered deep slip cluster. We observed a few reverse slipping events in this cluster, and these are recognized by these blue beach balls here, or focal magnums here. Let me walk you through the figure here on the very left end, are showing the waveform examples from a vertical component from one of the closest station to the cluster. And here I'm color coding all these waveforms, where the main shock with magnitude 3 is in red, and the aftershocks are in black. However, you may also notice within this 2 kilometer cube of the main shock, we also have some blue waveforms that is different from the waveform from the main shock. And they are different from the main shock in 2 ways. First, they have negative P wave polarity. And second, they have very weak Coda energy. So the figure here, figure B in the middle, are just showing the cross correlation between the waveforms. And when I generate this cross correlation or color plot, I made a little bit modification by searching for the largest absolute value, allowing for the maximum negative correlations. So in this plot, lighter color or white color means they are uncorrelated, whereas the blue color goes all the way to negative, means they're anti-correlated. So the modified cologram is confirming that there are some events that are similar to each other, but anti-correlated with the main shock. For example, the pair of earthquakes here with magnitude 1.25 and 1.19, they are a pair of reverse slipping events that are similar to each other, showing these blue focal magnums. And interestingly, the reverse events happened both before and after the main shock. So this is the main shock, and they happen both before and after. The figure D here in the upper right corner is showing, again, a depth view looking north. And from this figure, we can notice that most of these reverse slipping events happen towards the right side, which is the east side, suggesting all these reverse slipping likely occurred on a different branch of the main fault system. So such co-located but dissimilar events, on one hand, is supporting the complexity of fault system in the Raton, and on the other hand, it is also challenging the effectiveness of cross-correlation-based detection algorithms. So the topic itself may worth another talk, so I will just leave it here with a warning sign, and I look forward to discuss with you guys on the tricky frequency band about how sensitive they could be on the focal magnums. After going through the key complexity of each cluster, here is a bigger picture for the variable faulting, and this is my collection.
Can I ask you one question?
Yes.
Do you have any explanation why the coda is so low for the blue one?
Sorry, what's the coda is so weak?
Is there any structure, or why is it so different?
I think it might be, my best guess is related to the sum of the heterogeneity of the fault system that above it. So if you think about how the wave is propagate upward and maybe received by the station on the left side or on the westward, maybe there's more scattering than it's going to be observed directly from these fault systems that goes to that station. But I think I need to pull out more waveforms to answer that question, because I have an impression that if I pick a station on the other side of the fault system, the code are going to be weaker for the main shock, whereas stronger for these reverse slipping events. So they kind of like reflect.
Different. Okay, thank you.
Yeah.
Thank you.
Can you rule out depth?
I think the depths could be contributing, but if you look at the depth scale, we're looking at the difference only 100 meters. So I'm not sure how much contribution they
But
could
could there be
be.
a larger systematic error in depth for the reverse mechanisms? Those waveforms, they just look deep. You know, if I had to guess, just looking at the waveform comparison, I would say the blue traces look deep.
I think that's something I might be able to answer why I finished the cross correlation locations. So far, I'm using the arrival times to do the cross relocation. I think the relative error from hypo-DD is actually on meter scale. So I'm not sure if the depths could be wrong that much.
Yeah.
But I'd open to comments on that component. I don't have a solid answer to say yes or no. Thanks. Yeah. Okay, I guess I'm very excited to show this slide, so I cannot really wait to present this. This is actually my collection of the beach balls, and we're looking at two data sets here. So on the left side is zooming out to the whole basin, showing our 4-year catalog we obtained from 8 broadband stations. And here's the pink beach balls on the left I obtained from the full momentary inversions. And I should acknowledge Doug again for providing this package. And the figure on the right side, the red ones are from first motion picking. And these are results from the nodal array. So this is a hybrid sighting of our monitoring arrays and beach balls result from 2 different methods. And our ability to resolve the focal magnitudes are actually roughly 2 magnitudes larger than the magnitude of completeness. They are kind of like numbered here in the lower right corner. The reverse slipping events actually belongs to cluster 2, as highlighted by the blue box. I have walked you through them in the previous slides. And overall, we have consistent result from the 2 monitoring arrays and 2 methods. And if we zoom up to the northern part of the Raton Basin, the Colorado side, we also see the normal earthquakes are striking toward the northeast. So there's kind of like a further rotation of the strike angles of all these normal faults. And we can push the first motion analysis for the right side from the nodal array down to magnitude 0.5. And then we harvest 200 focal magnums. And they're color-coded by cluster from 1 to 3. So events falling outside of our defined cluster regions, falling outside of these 4 boxes, they're colored in gray in this case. So we are looking at about several dozen of focal magnums for each of the clusters. And that number of earthquakes, focal magnums, allows us to do a stress inversion. And the results are actually shown on the right side. They are also color-coded the same way. So here, the dip slip cluster is actually in blue, showing in the middle. And the vertical stress in our case is the largest stress, and is always a point, the vertical one, as located in the center of the mesh. The interesting thing we observe is moderate stress, which are the blue ones. In our setting, the normal setting, they should be corresponding to the maximum crustal stress orientations. And we are looking at the green stress orientations actually switching or rotating for 90 degrees from cluster 1 to cluster 2, where it's actually rotate back a little bit further south all the way to cluster 3. If we compare that to the well logging stress measurements from this region, for example, this is a figure from Yins. We actually have observed such rotation from these well logging results or records. because if you look at the Colorado side, we know most of the stress are actually from north to south, whereas outside the basin, if you look at these horizontal lines, they're mostly toward east to west outside the basin. So we kind of like know this stress rotation from previous stress analysis already, but it is surprising to us that such stress rotation actually happened within the basin, within a dozen kilometers. So that's as labeled by cluster 1, cluster 2, and 3 here. And these are the first order complexity we observed from these faults and focal maxims in a static way. And in other words, the beach faults we resolve are actually primary moment tensors, which only counts for the size of an earthquake and the orientation of the faults. We can actually push our source study to second moment analysis. And this method used here is taking advantage of a smaller event as EGF, empirical Green's function. So what we do is to decompose an EGF event from a master event, a larger event, at all the 3 components at a given station. And the figure here shows how the deconvolution is work. And taking advantage of the high quality data, this method modified after Jeff's MATLAB package from Ruijia worked pretty well. And I should have mentioned this process is semi-automatic in our setting because we are adopting all the phase picking or arrival times from the FaceNAC. We are not doing any manually picking or shifting when we invert for the apparent source time functions. And in this plot on the right side, each dot represents a station, and the black curves, the tiny wiggles here on top of them are the apparent source time functions resolved at each of the stations. The width of these source time functions are scaled with the rupture time as the color bar shows on the right side. So in the other word, the yellow to blue color means the longer to shorter rupture time. So from the color gradient, we can tell earthquake ruptured from north to south along the dip slope. And we are looking at a bimodal rupture from most of the stations in the north, whereas the bimodal kind of merge together and becomes a single peak toward the southern side. And for the size of the earthquake or for the fault, if we do a little bit inversion and calculation, it is about 300 meters long and less than 50 meters wide. The rupture velocity of this particular earthquake is comparable to the azimuth velocity in this region, just above 2 kilometers per second. The complex rupture is unique for cluster 2 though, as we did not observe any bimodal source time function from other clusters. The slides give you a few examples of the same second moment rupture analysis conducted for the other pairs. We're looking at a very short rupture time for cluster 1, whereas a moderate rupture time for cluster 3. This is for magnitude 3 earthquake. However, both of them are showing a single peak, which means that all the seismic energy are released in a single pulse. We're different from the cluster 2 that we are observing a bimodal rupture. And such variation in source time function have been long observed from larger events at a global scale. For example, the recent study by Yin et al. Collects over 3,000 source time functions of magnitude larger than 5.5 earthquakes over the world. And I think they found shallow events and strike slip events tends to have more multiple rupture phases like the cluster 2 that we have here. We are looking at the bimodal rupture. I think they also mentioned that if the strike slip event is sitting in a conjugate fault system, again, like the setting we have in Raton, they are more likely to have multiple rupture phases. I find it very interesting to supplement their data set with much smaller events from these injection-induced settings. And it's also interesting to think about like how natural these induced seismicity could be, just like the tectonic ones. So summing up for the complexity aspect, in addition to complex fault systems, complex fault geometries, we may also have kind of like a dynamic or variable stress and rupture behaviors in the Raton Basin. The complexity of these faults in the Raton Basin makes us wonder, is this variation related to industrial injection? Could we kind of find a connection between them? Or are the events just smaller earthquakes mimicking the complexity of tectonic earthquakes, just at a smaller scale? Well, that leads to the statistical analysis of the subclusters. And in the last few slides, I I will just show you how the complex events can still be explained by relatively simple statistical tools. And with that, I'd like to draw your attention to the first and basic method on the left side. So the figure here is just showing the Gutenberg-Ruijia law, where we expect a b-value of 1 from tectonic sequences. Some researchers have proposed that induced seismicity may have a different slope. However, this speculation is not true for Raton Basin, as our b-values for the slopes for these two clusters are still close to 1. So they are pretty similar to tectonic earthquakes. The figures here on the right side are just more fancy methods examining the inter-event time. The third column here is using ETAS, which is designed for tectonic sequence again, to model these induced seismicity. And we find ETAS can actually fit our seismicity rate pretty well. And you can also analyze that in the rescaled distance and time domain to look at the nearest neighbor distances between these earthquakes. And the take-home message here is we didn't really observe any induced nature or pattern for these two clusters. So overall, the injection-induced seismicity in the Raton Basin is just behaving like tectonic sequences from a statistical aspect. And here are the 4-year detection with 8 broadband stations. We are looking at over 30,000 earthquakes detected with magnitude down to 0. And this is work done by Margaret, a PhD student in our group. So I won't comment too much on the location then. They're pretty similar or comparable to our nodal array results. I just want to mention that if we apply the same 4 methods on the broadband catalog, again, we obtain a b-value of 1. Inter-event time less than 2, that's normalized inter-event time less than 2, and a well-fitted ETAS curve, and also the cluster in the nearest neighbor domain just fall below the diagonal and in this tectonic preferred region. So in the other word, the 4-year catalog, again, is just simply similar to tectonic events. And when we repeat such analysis to subsets of the broadband catalog, we see a little bit variation. Here, the regions are selected based on the fault zones. I'm showing 3 regions here. The yellow one is a Tasil fault zone to the west, and they are mostly the cluster 1 we have commented on. And the green one is the Vermejo fault zone, overlapping with cluster 2, 3, and 4 in our previous nodal arrays. And the blue squares, again, in the map are showing the wastewater injection wells. The statistical analysis for the 2 fault zones, here yellow and green, is nothing surprising. It's just similar and simple. However, the story changes and only changes when we go north, as highlighted by the red box. We observed a bimodal distribution where some earthquakes are behaving in a stationary way. And this is also the reason with increasing injection volume in the past few years. Such stationary behavior above this diagonal line means they are governed or driven by some external factors, for example, injection activities. And such distribution have been observed from other injection regions like the geothermal fields in California. So my interpretation for this red box for these behaviors is as some previous quiescent area starts to produce earthquakes, the fault system in the northern Raton Basin are actually developing its maturity under the wastewater disposal activities. So eventually, when the faults get closer to the critical stage, it will start to be productive and behave like natural sequences. So the injection activity is kind of jump starting the faults in the north, whereas the events in the southern part have been jump started. And so they are running like tectonic sequences with a lot of earthquake and earthquake triggering between them. And lastly, from our 4-year detection, we were able to confirm that the Trinidad fault zone is no longer active. The shutdown could be associated with recent decrease of injection activity around it. So the variable statistical behaviors and faults and clusters may be still linked back to different stages of maturity and eventually related to the injection change in the Raton Basin. So in summary, machine learning and our hybrid array bring our monitoring ability to another level. we unveil the complex fault system and observe variable behaviors from different clusters. These magnitude less than 3 earthquakes are no longer a point source. They are not in space, not in time, and sometimes not repeating. So despite the driven force from wastewater injection, we are looking at some events that here follows a statistical behavior of the tectonic sequences. So I'd like to thank my co-authors and collaborators here. And in addition, if anyone is interested in trying the detection and location workflow, we all have made the logflow package open on GitHub. It has been upgraded and renovated, aiming to provide easy and seamless communication between these wonderful packages developed by our pioneers. So it comes with a cookbook, and welcome to try it out. So thank you for your attention. I'm happy to take questions here.
I had two quick questions, or maybe one quick question and a second question. So when you're saying bimodal rupture, are you meaning bilateral, or are you meaning bimodal in the sense that it's rupturing both of the orthogonal planes?
Lateral. I think it's on the same strand. Okay. Yes.
And then you have quite a few moment tensors. Do you see any evidence of volumetric changes?
I know you're gonna have that question. And this is what they look like on the limb plot, where we do see a certain amount of positive volume increase and a little bit on the tensor crack opening. I think some from a statistical way, but I'm not sure if my moment tensor fitting is that good to make a conclusion on individual events.
Are you planning to kind of zero in on any given point and try to assess uncertainty in things like the volumetric component or other?
I think I should be, and but I didn't really get a time to revisit all these lovely beach balls for now. But let's say that's on the plan.
Okay, thanks. So thank you very much, Ruijia. Very interesting work. And well, let's thank Ruijia again for my talk.
Well, thank you.
Yeah, thank you
Guess
very
you
much.
all have a great seminar and yeah, great term.
Thank you.
Thank you.